Welcome to State of Simulation, the podcast all about multiphysics simulation, where we stay up to date with what's working, what's not, and what needs to change. Each episode features an open conversation with the engineers and technical leaders shaping the future of physical product development. I'm your host, Jukka Knutinen, and in today's episode, we're speaking with Martin Angerer, Postdoctoral Research Engineer at the University of British Columbia, specializing in MEMS ultrasound technology. With experience in both industry and applied academic research, Martin has worked on modeling, rapid prototyping, process optimization, and testing of MEMS sensors and acoustic transducers. In this episode, we explore how ultrasound transducers are developed, from the fundamental electromechanical conversion to MEMS-based prototypes to the simulation workflows that support them. We cover how finite element modeling, analytic approaches, and rapid iteration play into the design of sensors, what the current simulation strengths and limitations are, and where things are headed. Without further ado, let's get started with the show. What is a ultrasound transducer, in your own words?
Well, it's basically a device, electromechanical converter, basically something which converts electrical energy into, in the end, acoustic energy, and ideally always vice versa. So you basically can transmit acoustic waves and on the other side receive it and convert it into an electrical signal.
What is the role of this? So where are they used and what do they do in practice?
I mean, basically, it's an acoustic converter. So ultrasound means basically outside the audible spectrum, so higher frequencies. So in general, the ultrasound waves require medium. So you basically send something out and can receive something back. And depending on the nature of the material, you're basically sending these wave throughs, you get reflection. And from there, you can estimate what is actually in a material, or also in air, certain distances, certain changes in acoustic properties. Hence, it is a good opportunity and a good modality to do cross-sectional imaging, which is often used in medical imaging, but also lots of industrial applications for that.
I'm sure everyone, most if not everyone, knows about the medical side. So what are then the sort of non-medical industry applications of this?
Well, there's a variety of different applications. I mean, it's not just for inspection. So ultrasound is actually also used for welding, for example. So high power ultrasound, which induces a lot of energy to melt, for example, plastic composites and stuff like that. But typically it's used for inspection. So acoustic signals are generated if materials degenerate, break, and so on. So this is often done with non-destructive testing purposes. So you assess if something goes wrong in the structure in the material by reading out acoustic signal like shear waves or longitudinal waves running through the structures. But also it has a variety of applications. So you can do good flow detection with it. You can do a quite new topic, also do particle detection in fluids and also in air. So it is an interesting modality. And I think one of the key benefits is very simple, very easy, very low power, and inherently benign. So there is no radiation and no, let's say, negative or no strong negative effects. Depending on the heat, maybe it induces if it's high power.
All right. So what I understand is that there are different types of ultrasound transducers. Which ones are you most interested in?
So my background is, well, I come more from the piezoelectric part. So piezoelectric crystals, very old technology, has been discovered decades ago and refined over these decades. But eventually I shifted to micromachined transducers, and they're specifically polymer-based micromachine transducers. So yeah, well, with those, there's lots of things to explain about those. So in general, micromachine transducers, the general physical principle should remain the same. So we want to build something which converts electrical energy into mechanical energy and vice versa. So typically with a piezo, it's done piezoelectric effect. So basically you apply a voltage and then the material deforms and generates a mechanic deformation. This in the end is translated to an acoustic signal. And when an acoustic signal interferes with the piezoelectric crystal, then it deforms and creates an electric signal. So how to do that now with other ways? So I think about maybe a bit more than 20 years, researchers came up with the idea, why not to produce very small membranes? So basically like drums, which can be electrostatically or piezoelectrically driven to deform and so generate an acoustic signal and receive an acoustic signal. And with the rise in MEMS technology, so photolithography and silicon microfabrication, this started to become very feasible at some point. So researchers made great effort in order to mature this technology. And silicon-based so-called CMOS, so capacitive micromachined ultrasonic transducers, are now reaching a commercial stage, I think, while on the other hand, so not electrostatically driven with a capacitive behavior, so piezoelectric driven with a thin film, are still under heavy investigations, but there is perhaps quite some companies producing those. And we came up, our group where I joined a few years ago came up, why not produce these microscopic drums using polymer layers in additive processing, so layer on layer, and then in the end form these microscopic drums.
So what makes that approach special or useful?
I mean, I'm heavily biased, obviously. So in my opinion, I mean, I worked for many years now in the ultrasound field. It's actually kind of hard to get dedicated transducers, like prototype transducers, which fit your specific acoustic requirement. These can vary depending on the application. For example, in imaging, there are different imaging modalities, imaging approaches, where you need specifically tuned acoustic properties to those. And in order to get transducers which best match these properties, it's actually quite expensive to do prototyping. Piezoelectrics, yeah, major technology, but they have their inherent limitations. Like you can't make them very, very small. 3D integration is a little bit of a challenge. And like the aforementioned micromachined transducers on silicon base, it's produced with manufacturing processes similar to chip manufacturing. So it takes time. It takes a lot of effort, it takes time, and the costs are very high. So by using these polymers now, we can speed up significantly fabrication. So we can, within a few days, we can produce very, very specialized and very dedicated transducers to a specific requirement or environment.
Okay, if we go a few steps back and start from the idea of a new kind of sensor. So could you walk us through the sort of workflow or the process of how it turns from just an idea or a concept to an actual first prototype? What happens in between?
So yeah, there's, as with the background of this podcast, there's a lot of modeling included. So in the end, I mean, as always, it's no difference, I guess, in research as an industry. So at the beginning, you quite have to clearly define your requirements. So what is your system supposed to do in the end? So what you need in terms of, for example, acoustic fields, acoustic sound pressure, frequency ranges, and so on. And there's quite a lot of requirements coming in, depending on the application, as I said. So is it a 3D? Is it an imaging application? And so on. So you derive based on best knowledge you have at the moment, you derive the requirements you need for the system. So you say, now, okay, that will be my ideal acoustic field. So how to, in the end, translate this knowledge then into the actual transducer design? And this is where the modeling part comes in, which is essential, even for a technology like we have, where, as I said, the turnover time and the fabrication time is fairly quick. It's still important to know as good as you can the design choices you will make and reflect on that before you actually go into production.
Yeah, so that's actually something that is of particular interest for me. So when you have a design of some sort and you are confident that it might be suitable based on the wanted parameters that you identified at the start. So how are you sure in your current approach that is the best choice or a good choice? And like how many choices do you compare to in that process? Overall, basically what I'm getting at is how thoroughly are you in your current processes basically investigating the design space?
So for us, I think we started that journey now a few years ago when we really started to look into modeling. You know, it's a technology which has a quick turnover time and quick prototyping, also has a little bit, you know, you neglect a little bit the actual modeling or the design because you say, we're so quick, we just produce another one. But in the end, you end up with try and error. And this is actually what happened a lot in the past. And even with quick turnover times, try and error is no good approach. So you waste a lot of money, you waste a lot of time, and you get frustrated at some point because you don't understand what is actually happening. You don't make progress. So in the end, it's actually quite important to model as accurate, at least in my opinion, as accurate as possible, the final design. So you have the design choices. Of course, there are realistic there are fundamental limitations. So you can't say, okay, yeah, the acoustic field needs to be infinite high, just as an example, because that's just physically not possible, at least. So I guess there it becomes very important that you are built based on your experience, a system which is actually feasible with the technology you use, and then you start tweaking on all the different design parameters. So for example, like a Micromachine transducer, like I said, these small drums we're producing, they have a lot of different design opportunities and parameters. So how thick we do the layers, how big we do them, how big is the diameter, how do we arrange these cells in order to form a macroscopic acoustic cell, how we arrange them finally then in an array and so on. So this adds up to a lot of different design choices where you start to get a feeling over time, obviously, but in the end, you actually have to permute everything through certain models. Through models you build up. Usually you start very simple, and then in the end, you make them more elaborate and more elaborate. And in the end, to really define the acoustic properties based on the design inputs you choose.
Okay, so for as the nature of the podcast, state of simulation,
yeah.
What is the state of simulation currently in your field? So how does it serve you? What are the pros? What are the strengths, and vice versa? What are the cons or the limitations that you're facing?
So yeah, I mean, there's a variety of different approaches. I mean, I think initially, typically one starts with an analytical approach. So equivalent circuits. I mean, it is used a lot, especially in electromechanic resonator. It's a very useful tool going with fairly simplified, like Butterworth-Van Dyke filters, which is basically just a structure of passive components, which mimics your performance. And those already give you a fairly clear idea what the initial design choice is supposed to be. So from there, from the analytic approach, you typically start. And then, I mean, at some point, analytic approaches, there's always fundamental limitations. So as soon as, for example, shapes become more complicated, the analytic formulations become very complicated or even not solvable. And then since we have a lot of physics in it, so we have to convert from electrical to mechanical energy, and then finally to acoustic. There's a lot of physics, and that simplifications for analytic formulation required. So at some point, the simplifications leads to inaccurate results. Hence, from the analytic approach, eventually you typically go to a numeric approach, like I typically use finite element. And there's a certain, so I also use a lot of combinations of those to simplified simulations of finite element and then feed it into equivalent circuit models. So this is possible. But eventually, larger scale finite element models give you the most thorough representation of the system or how it's supposed to behave.
All right. So building on that, it's sort of became to be the classic question of the show. So if you had a magic wand which you could zap, and you could just do one thing, so it's just improve one area of your current modeling capabilities, which would it be?
So yeah, there are a few things. I mean, I like always to do the entirety of the simulation, basically to model the entire structures, and then in the end do this translation into acoustics, which requires lots of fine structures like micromachined. In the end, you have to resolve millimeters, or micrometers, even nanometer thicknesses, and then in the end go to a bigger acoustic problem. So the models become very big. So at some point, doing real-time analysis of big models really helps. So it really shows you how it's supposed to do. And then in the end, yeah, scalability is a thing, because I mean, at some point, it's not just one transducer, it's more transducers. Like typical medical imaging ultrasound arrays have 192 ultrasound transducers in one array. Then 3D applications go to thousands and thousands and thousands. And yes, maybe not all of them need to be modeled completely accurately, but in the end, the more accurate, with a simplified tool, you can predict your acoustic performance while still having the opportunity to feed all design choices in the first places. Would be tempting. Yeah.
All right. Well, I'm sure you are keeping a close eye on the field and overall these sort of emerging technologies that are going on right now. So anything in particular that you're keeping an eye on that could help you later on?
I mean, yeah, cloud computing is constant use. I think this is a good path towards scalability. I mean, with the RISE, we use also lots of cluster computing for the larger simulations, while I try to limit the large simulations always to the final design choices. So try to do as much as I can with simplified models, with shrink down models, with implementations and skipping a few physics. For example, you can mimic electromechanic conversion by just feeding into an acoustic problem, using piston radiator models and stuff like that. So this really helps. So in the end, then going to the large scale just in the end, and I think this is a trend more people do, but I see a trend also in more accurate simulation, especially when it comes now to the 3D fields. I mean, for example, in medical imaging, the 3D or the 2D arrays for 3D ultrasound imaging, I think, are reaching now maturity. So they will start to penetrate more and more the markets. But there it becomes more and more important to understand the system behavior. So it's not just one transducer, but how do they interact? How is the crosstalk and so on? So crosstalk meaning basically the transmission from the unwanted transmission from one transducer to the next and so on. So system-based simulation, I think, is where more and more people are interested in.
Interesting. How about the number one hype that seems to be in all of the fields, like and I mean literally all of the fields. So AI, machine learning, what kind of opportunities do you see there?
Cool. I mean, interestingly enough, I've been recently to the main conference. I mean, in terms of design, I actually haven't seen much AI influencing design choices. I mean, AI is used as a support tool, as an explanatory tool. It helps you to interpret a little bit better the results, but really leveraging models into your design process, I haven't really seen. So, for example, using a network model, which would significantly simplify your design approach, that would be very interesting, but it has to be somehow physics-based. So I think this is where there is some work now emerging, but not sure. I mean, a current trend is now acoustic holography, so building arbitrary 3D fields and acoustic fields in 3D. And there you can imagine, I mean, forming the acoustic field with variations of transducers is inherently complex. So I reckon AI approaches or network models using machine learning aspects will come into place eventually.
All right. Well, as the last question, is there just anything in particular that is currently of interest to you, or just a topic that you find fascinating, whether it be in your current day-to-day job or on your field, in your field, or anything else that you are sort of dabbling in, anything that you find particularly fascinating?
I mean, I must say the thing I just mentioned, the acoustic holography, so the generation of 3D fields, which allows also particle levitation, is exciting. Because in the end, it is let's say from a design choice, it is a challenge because you have to arrange. I mean, it's not just the transducers, which always generate acoustic fields depending on the size and so on, but you have to arrange them in a very smart way to play everything together. So design input, design choices, but then arrangements, distances, frequencies, medium you use in there. And this offers a lot of potential applications, I think. I mean, if we just not only think of just levitation, I mean, maybe some people already saw some of the videos where styrofoam balls are levitated in air. Very exciting, but there are lots of technical, practical applications where you could, for example, levitate cells into a 3D medium in order to use manipulation on those and so on. So I think there is a lot of interesting stuff coming in this aspect. So I'm fascinated by that approach.
All right. Well, thank you so much for joining. I had a wonderful time talking with you.
Thank you very much, Yuka. It was a pleasure talking with you.
Thank you for listening to this episode of The State of Simulation. To stay updated with the latest episodes, webinars, blogs, white papers, and more, join our community of more than 7,000 engineers and engineer-minded people on our LinkedIn page, Quonscient. Thank you again, and see you in the next one.